about linear dependence and linear independence. So we first define what we call a linear combination of vectors. Of course, from now onwards, we'll be looking at the structure we discussed last time, which is a vector space. So if we have a vector space V, and definitely it's a non-empty set together with two operations, addition and scalar multiplication, satisfying the other list of 10 properties. Now, in this non-empty set, there are elements. The elements are called vectors. So we define what we call a linear combination of these vectors. So if there is an element X in that vector space V, then so we define the vector X as a linear combination of vectors X1, X2 in V. Remember, X1, X2 up to Xn depends on the dimension of the vector space V. We shall later on define the dimension of the vector space, but I showed you when we met physically what we mean by the nature of elements in R2. They are two-dimensional. Nature of elements in R3, they are three-dimensional. So this vector here is a linear combination of these other vectors if X can be written as alpha 1 X1 plus alpha 2 X2 plus alpha 3 X3 plus and so on up to alpha n Xn, where alpha i's are scalars. That's what we mean when we talk of a linear combination. Let's get a quick example here of a linear combination. We have vectors 2, 1, 5, -5 in R4. You see, they are 4 dimensions, so they are in R4. And we want to write it as a linear combination of 3 vectors. This, and that, they are also in R4. So to do that, to write it as a combination of those vectors, to write that as a combination of those vectors, we just get this vector here. Remember, just look at this. Okay, yeah, just look at this one here. X is alpha 1, X1, and so on. This is what we call a linear combination. So likewise, we write this is equal to alpha 1, the first constant, times the first vector, plus alpha 2, the second constant, times the second vector, plus alpha 3, the third constant, times the third vector. Now, to write this as a linear combination here, we need to solve. We need to find suitable values of alpha 1, alpha 2, and alpha 3 so that this equation here will hold true. Now, how do we find the values of alpha 1, alpha 2, and alpha 3? We just solve. We equate coefficients actually. This is alpha 1 plus alpha 2 plus alpha 3 is equal to the first entry here. The first entry times alpha 1 plus the first entry here times alpha 2 plus the first entry here times alpha 3 is equal to the first entry here. So we get this first equation. Then the second entry, alpha 2, that is 2 alpha 2. Here we have, 2 alpha 1. Here alpha 2 is 0 because the second entry is 0. Then plus alpha 3, that one should give us 1. So alpha 1 plus alpha 3 is 1. The second entry here, for alpha 2, it is 0. Then the third entry now, this is alpha 1 plus 2 alpha 2, then alpha 3 is 0. So that one gives us 5. And lastly, gives us 5 because 5 is the third entry here. Then the last entry, this is minus alpha 1 minus alpha 3 minus alpha 2 is equal to minus 5. So we get a system of 4 equations. We get a system of 4 equations and we have 3 unknowns. So that means when we solve that system, we can just write it we can solve it using the methods of solving systems of equations, which we look at in chapter 2. Then we get alpha 1 as 1, alpha 2 as 2, and alpha 3 as the negative 1, and alpha 3 as negative 1. So that means that we can now write our vector. It means that this vector here is the alpha 1 is 1, alpha 2 is 2, alpha 3 is that. So it means that uh, the vector, so it can be expressed in terms of those vectors. Thus, it's a linear combination. That's what we mean by a linear combination. Let's have a look at another quick example. We have polynomials, a polynomial. Last time we looked at a vector space which we call P2 or P3, which is a vector space whose elements are polynomials of degree less or equal to 2. So we have this polynomial. It is t squared plus t plus 2, and is defined over R. It means the coefficients are real numbers. We want to write it as a linear combination of these two polynomials, P1, which is 2t squared plus t, and P2, which is 3t squared plus 2t plus 2. So we solve for the constants alpha 1, alpha 2, such that P alpha 1, such that you see P, this is what we want to write as this linear combination. So constants alpha 1, P1, alpha 2, P2. So this is the polynomial, then this is alpha 1, this is that. So it means we work towards finding the values of alpha 1 and alpha 2. And here we can equate coefficients, you see. This is the 2 alpha 1 plus 3 alpha 2. All these are coefficients of t squared, so that one will be equal to the coefficient of t squared in the left-hand side, which is 1. Then alpha 1 plus 2 alpha 2. These are coefficients of t, so those ones would be equal to 1, which is the coefficient of t here. Then this is 2 alpha 2 is a constant term here. In the polynomial, we don't have a constant term. So 2 alpha 2 should be equal to 2 because 2 is a constant term here. So when we solve this system, it automatically means when we divide here by 2 alpha 1, alpha 2 is 1. And when we substitute it here, it means alpha 1 is negative 1. So it means our polynomial can be written like this as a linear combination. As a linear combination. As a linear combination. Okay. Members, are we okay with linear combination? We have defined a linear combination of vectors. We are saying that that a linear combination, we define a vector x to be a linear combination of vectors x1, x2 up to xn, if x can be written in that form. That's what we call a linear combination. Are we okay with the definition of a linear combination and the two examples we have seen? Remember?
Yes, sir.
Okay, good. Now, here is another example. This is a vector in R3, it's three-dimensional. So we want to write it as a linear combination of three vectors here. So we just write a linear combination. We equate coefficients as usual. Alpha 1 plus 2 alpha 2 plus alpha 3 is the first vector to form this system of equations. And when we try to solve this system of equations, it is inconsistent. It is inconsistent. We have three cases which we find in chapter 2 of solving systems of equations. Now, by inconsistency here, it means that we can, these unknowns cannot be solved. The system has no scalars alpha that satisfy the relation. That means we cannot express the other vectors, the other vector as the other vector is not a linear combination of these vectors, because when we try to solve, we can't get the values. Now we have defined a linear combination. So a vector X can be written as a linear combination if there exists scalars alpha 1, alpha 2, up to alpha n, so that we can write the other X, vector X, as a linear combination with other vectors and uh, and the, and the scalars. Of course, just like the words are just linear on a straight line. So a combination. So we write a vector as a combination of scalars and other vectors. Now, let's define what we mean by a set S spanning the vector space V. Now, let V be a vector space and S be a set with vectors x1, x2, up to xn. We say S spans V. We say S spans V, or V is spanned by S. We say S spans V, or V is spanned by S, or V is spanned by S, if every element of V can be written as a linear combination of elements in S. You see, now we know what a linear combination is. Now we are saying if this set S with these vectors, such that every element of V can be written as this linear combination, then it means S is called a spanning set of V, or S spans V, or V is spanned by S. In other words, if every vector E belonging to the vector space V is a linear combination of all vectors in S, so this is the other way of defining a spanning set. If every other vector E belonging to the space V is a linear combination of all vectors in S. So if S is this and V is having these elements, then we see that the dimension of S is the same as the dimension of V. Therefore, S, the spanning set, is normally a subset of the vector space. The spanning set is a subset of the vector space, and every vector EI, this EI is a representative of any element we can pick here. Every vector EI can be written as a linear combination of vectors from the spanning set. So we have an example. We want to show that S spans V. S is a set which has 1, 2, 3 elements in 3-dimensional. V is R3. V is a set of all quadruples. No, are they triples? They are triples. Triples. 3 dimensions. So you see, even every element of S is 3 dimensions. So we want to show that this set with 3 elements here spans V. What does it mean by this set spanning V? It means that every vector in V can be written as a linear combination of these elements here. Every vector in V can be written as a linear combination of these vectors here. Okay, we choose any vector. Let A, B, C be a vector in R3 or in V. Because now we want to show that every vector in V can be written as this linear combination. So we choose a representative of all. We don't choose a specific vector, but we choose a general vector in R3 with A, B, C. So to show that we can find constants alpha 1, alpha 3, because there are 3 elements here, such that every element here, this representative element, can be written as this linear combination. We simply need to form the other equations like we did before. And we need, if this system here is consistent, if this system here is consistent, if this system here is consistent, then it means we can find these vectors, and it means every vector in V can be written as a linear combination of elements from the spanning set. Now, when we solve this system, when we follow reduction to echelon, get this, and this means that the alpha 1, alpha 2, the constants are defined. It means that the constants are defined because here we can, when we are doing back substitution, this means 3 alpha 3 is equal to 4b minus 2ac. So it means since after row reduction to echelon, we have this kind of nature, then it means the system is consistent, and by the system being consistent, it means that we are able to find the scalars alpha 1, alpha 2, such that this linear combination holds. So that means S spans V. That means every vector in S can be written as a linear combination of elements or vectors from the spanning set. Let's check another example. Here we have C is a space of all polynomials of degree less or equal to 2, and S has 2 elements. The elements in S are also polynomials of degree less or equal to 2. So we want to show that this set spans the entire. It means we want to show that every polynomial of degree less or equal to 2 can be written as this linear combination. So how do we do that? We let at squared plus bt plus c. This is a polynomial of degree less or equal to 2. Be a polynomial of degree less or equal to 2. So you could have chosen you could have chosen this, you could have chosen this, and so on and so forth. And any, provided it's a polynomial of degree less or equal. But we usually consider the general case. That's what I was talking about. This is a general case. So we write it as a linear combination. Then we generate this system here. We generate a system here. And when we solve this system, definitely alpha is b over 2, beta will be that. So it means this system is consistent. That's this. Okay. Okay. Alpha is this, beta is this. Then alpha will be, you see, the system is inconsistent. There are no two values of alpha. You see, here we have alpha, but when we try to solve here, we get a different value of alpha. That means the system is inconsistent. So the coefficients do not exist, and that means that this set here cannot span, this set here cannot span every polynomial of degree less or equal to 2. Okay, now I've talked a lot. I've defined a spanning set, and I've given 2 examples of a spanning set. We've said a set S is said to span a vector space V if every element from V, from the vector space, can be written as a linear combination of elements from V. Are we together, members?
Yes, please.
Okay, okay. So we've defined a linear combination. We have defined a spanning set. We now know what it means by a vector being written as a linear combination. We also know what it means by a given set spanning. So we have an exercise, write the polynomial t2 plus 1 over r as a linear combination of polynomials here. This can be done. Check whether the matrix A can be written as a linear combination of these other matrices, B1, B2, B3, B4. Yeah, it can happen. And here are the constants. If you try to solve, you should get these constants. Okay. 5, V is R3. Which of the following sets span V? What does it mean by spanning? It means that every element here can be written as a linear every vector in R3 can be written as a linear combination here. So we can always check that. So now that we know a linear combination and a spanning set, we are now set to define what we call linear dependency. We are set to define linear dependency and linear dependency. We are set to define linear dependency and linear dependency. Bosco, I see a stranger in our class. Bosco. Bosco, can you talk to me? I don't know. Bosco, okay?
Hello, good morning, sir. Yes.
Good morning.
I thought this is our class, sir.
No, this is not
I'm
our
okay, sir.
class. I'm still in
This is not our class.
Okay, sir, I'm sorry.
You send me, do you have my WhatsApp number? Bosco. You have my WhatsApp number.
Yes, I have.
Yeah, send me a WhatsApp message.
Yes.
Then I'll link up.
Okay.
Okay, so members, linear dependence and linear independence. Now, if S is our spanning set, which is a k-dimensional X, which has a k elements, x1, x2, x3, up to xk. And for every vector xi in V, then S, the spanning set, is said to be linearly dependent. So we are defining what it means by a set being linearly dependent. We have a set S, and that set is said to be linearly dependent if there exists, if and only if there exists. Now this if and only if means that if these constants alpha 1 up alpha k, not all zeros, such that the linear combination is 0. If we write the linear combination of this set with constants alpha 1, alpha 2 up alpha k, and it comes out that not all the constants are zeros, yet the linear combination is 0. Not all the constants are zeros, yet the linear combination is 0. It means that the set is said to be linearly dependent. We have a set of constants, not all of them zeros. We have a set of constants, not all of them zeros, but the linear combination is 0, then that set is said to be linearly dependent. One can be expressed in terms of others, i.e. depends on the other. That's what linear dependent. Otherwise, it is linearly dependent. That means a set is said to be linearly independent if the only time this linear combination is equal to 0 is if all the constants are zeros. But if we write a linear combination and we find all the constants are not zeros, yet the linear combination is 0, then there we get linear dependency. Okay. Now, linear independency, we are saying we have a set S as usual, then S is said to be linearly independent if and only if this linear combination is equal to 0. Okay, there's a 0 missing here. I think the scan missed the 0 here. If the only time this linear combination can be 0 is when all the constants are zeros. Let's check we want to show that this set S here is linearly independent. Now, alpha 1, we write the set as a linear combination and equate to 0. You see, this is 4 dimension, so even the 0 will be in 4 dimension. When we equate to 0, even the 0 here will be in 4 dimension. So when we do that, we generate this system. And when we try to solve this system, we find that all the constants must be zeros. So that means that this set here is linearly independent, because when we write it as a linear combination of constants alpha 1, alpha 2, the linear combination can be 0. The only time this linear combination can be 0 is if all the constants are 0. So that means it is linearly independent. We have another case, another example. A set, have this set. I want to show if it is linearly independent or dependent. We just simply need to write this linear combination, equate it to 0. But now the 0 here should be in 3 dimensions. So we generate this system of equations, and when we solve this system of equations, we find that we have many unknowns than the number of non-zero rows after reduction. That means this system will have infinitely many solutions. It has infinitely many solutions and not only zeros. So it means the solution may not only, so it means they are non-zero values of alpha 1, alpha 2, for which the linear combination is 0. So this implies linearly dependent. So members, are we together with linear dependence and linear independence?
Yes, please, sir.
Okay, now we can stop here for now. We can stop here for now. Yeah, we can stop here for now. Then tomorrow we shall continue. I think the notes we have end here. I'm going to generate for you something else. I am not so sure if we are able to meet tomorrow. Okay, we shall discuss. But for now, we've discussed what it means by a vector to be treated as a linear combination. Now that's one. We've discussed what it means by a set S to span a vector space. We've also discussed what it means by a set S to be linearly dependent or to be linearly dependent. And now we are just laying a foundation. You'll find you'll meet these words, these terms. You'll just keep using them in most of the mathematics that you need ahead of you. So please make sure you concentrate. There are so many exercises here. I would have added you an assignment, but you told me really overloaded. Let me leave you to concentrate. But please make sure if you find time, try to work out some of these things. Try to, if you get any challenge, my inbox is open. Just drop your question there. I will respond to it. Please prepare for the test on Thursday when we meet, and let your assignment be ready for submission. Is that okay?
Please. Okay, thank you, sir.
Okay, please. Have a good day. Let's meet next time, probably tomorrow.
Okay.